Welcome to the video explanation for Griffiths problem 6.15a. So going into a brief description of the problem, it tells us that we have to determine the lowest order amplitude for the process a plus b to a plus b, which is a process in ABC theory. So the problem tells us that there are two diagrams, and I went ahead and drew them right here. So these are the diagrams that we'll be determining the lowest order amplitudes for. And the reason why we want to find these amplitudes is because the amplitude contains all the relevant dynamical information for these processes. So they're of great relevance and great use for us, which is why we want to find them. Okay, so let's go ahead and find the lowest order amplitude for the first diagram. That is the one on the left. So we're going to be following a 6-step process to determine the lowest order amplitude of each of our two diagrams. And so the first step of the recipe is notation. We have to label the incoming and the outgoing form momenta in the diagram. And each form momenta is given an arrow to keep track of the positive direction. So forward in time for external lines and arbitrary for internal lines. So if we have a look on the right side, the two diagrams, the incoming momenta are given the names P1 and P2 with directions going forward in time, and the outgoing momenta are given labels P3 and P4, also with arrows going forward in time. And then for the internal momenta, I labeled that Q1, and I just chose the direction for the arrow as upwards arbitrarily. It could have been downwards, it doesn't really matter. So next step in the process is vertex factors. So for each vertex, we write down a factor of minus ig, where g is the coupling constant. So since there are two vertices in the following diagram, we write down minus ig squared. The third step of the process involves propagators. So for each internal line, we write down a factor of I over qj squared minus mj squared c squared, where qj is the form momentum of the line, and mj is the mass of the particle that the line describes. So the label for our internal line is q1, and we only have one internal line, so we write down one factor, which would be I over q1 squared minus m1 squared c squared. Step 4 involves conservation of energy and momentum. For each vertex, we write down a delta function of the form 2 pi to the 4, delta to the 4, k1 plus k2 plus k3, where the k's are the three form momenta coming into the vertex. So if the arrow leads outwards, then k is minus the form momentum of that line. So let's take it nice and slow. For example, let us look at the top vertex in the diagram. So looking at the top vertex, we can see that P1 and Q1 are both entering the vertex, while P3 is leaving the vertex. So we can see right here in this middle term, we have 2 pi to the 4, delta to the 4, and then P1 and Q1 are positive because they are entering the vertex, and P3 is negative because that momentum is leaving the vertex. And so we actually follow a similar process once more for the second vertex. Step 5 is integration over the internal momenta. For each internal line, we write down a factor of 1 over 2 pi to the 4, d4 qj. So once again, we only have one internal line, and hence one internal momenta. So our last term on the end would be 1 over 2 pi to the 4, d to the 4 q1. Essentially what we're doing here is we're tacking on a differential so that we can integrate over the internal momenta. So then we add an integral to the left side of the expression, and all of this whole integral is equal to the lowest order amplitude for diagram 1. So now all there is left for us to do is to evaluate this integral. So before we do that, actually, we're going to do some cleaning up just so that the integral is a bit easier to work with. And so what we can do here to evaluate this integral is to use the Dirac delta function. So we're going to use the Dirac delta function to collapse it, and so we're going to use the following Dirac delta function trick, if you will, on the right-hand side. So the integral of the Dirac delta function can just be written as the function evaluated at A. So for the process that we were looking at before, we're going to replace Q1 with P3 minus P1. And in our case, if you're going to match it up with the format on the right-hand side, X is Q1 and A is P3 minus P1. So what does it look like once we apply the direct delta function trick? We get the expression on the bottom, and so the direct delta function is really nice because it kills off the integral, and now we are left with the last expression, and at this point we can use we can go to step 6 of our recipe, which is the final step, which is to cancel the remaining delta function. So step 6 tells us that the result will include a delta function 2 pi to the 4 delta to the 4 p1 plus p2 all the way to pn, and this reflects the overall conservation of energy and momentum. And so step 6 says just erase it. So as we can see in the numerator of our expression, we can see that there is indeed a remaining delta function with the whole 2 pi to the 4 delta to the 4 and everything. So we're going to just erase this and then multiply our remaining expression by I. And that's it. So we get the amplitude of the first diagram being g squared over p3 minus p1 squared minus m1 squared c squared. Nice. Okay, so now let's move on to the second diagram. So the process is actually the exact same. We follow the same 6-step recipe, and we will get the lowest order amplitude for the second diagram. It's going to be slightly different in terms of just because of the orientation, I suppose, of the Feynman diagram, but the process is going to be very, very similar. So I'm not going to go through a lot of the detail because I already went through it one time. I'm just going to briefly skim over the steps. So step 1 is notation, where we label everything, all the momenta, the incoming momenta, the outgoing momenta, and then the one internal momentum in the center with P1, P2, P3, P4, and the internal momentum as Q1 with the corresponding arrows. Then we write down vertex factor. There are 2 vertices for this diagram, so then we write down minus ig squared. Next, we add in a factor, or we multiply in a factor of I over qj squared minus mj squared c squared for each internal line. We only have one internal line, just like in the previous diagram, so we multiply by one of those. Step 4, we write down direct delta function of the following form, where once again the 3 4 momenta coming, where it models the 3 4 momenta coming into the vertex. So if the arrow for the momentum leads outwards, then the k in the expression is minus the 4 momentum in that line. So I'll just do one example again on the left. There are 2 momenta going into the vertex, so it's p1 plus p2, so these will be positive, and there is a q1 internal momentum that is leaving the vertex, so that's going to be negative. And this is reflected in this term right here, the center term, where you have p1 plus p2, these are both positive, and the last internal momentum is negative, minus q1. Lastly, second to last, we're going to integrate over the internal momenta, and so we tack on the factor of 1 over 2 pi to the 4, and then the differential, and then we actually integrate. So we're going to use the same trick that we did last time, use the direct delta function, kill one of the integrals, and then we replace q1 instead of whatever we used before. We're going to replace q1 with p4 plus p3, where once again q1 is the x in the previous format that I mentioned, and p4 plus p3 is a. So then we get the expression as shown right at the bottom. And lastly, we can proceed on to step 6 of the recipe, which is to cancel the delta function. So the remaining delta function we can see is 2 pi to the 4, delta to the 4, p1 plus p2 minus p4 minus p3. So we erase that, multiply the last expression by a factor of I, and then a bang bang, we are done. So we get the amplitude for the second diagram, and it's found to be g squared over p4 plus p3 squared minus m1 c squared. And that is all. Thank you.